Hi guys, and welcome back to my garage. In tonight's video we're going to be talking about TPS, APP, TAC, and DBW, and what these acronyms mean and what these systems are all about. Okay, so in yesterday's lesson we learned about potentiometers and rheostats. We learned that a potentiometer is a fine little 3-wire position sensor that we can use to monitor the position of things. So we're going to talk about that technology again in a TPS, by the way. P does not stand for potentiometer. And we're going to find out why we need these things and how we employ this technology and how we have kind of progressed this technology through the years. Okay, so for starters, a TPS is a throttle position sensor. It is a potentiometer. As we learned yesterday, a potentiometer has 3 wires. One wire is going to supply some power to this sensor. One wire is going to be a ground for the sensor, and the third wire is going to be the signal that returns to the computer. Okay, so why do we need a TPS? Well, let's start back with carburetors. So way back when we had carburetors, this was a carburetor here. This one I used in a previous video. It was actually originally applied to a forklift. This is a forklift carburetor. We naturally had a cable that connected your throttle to the pedal, or on a forklift, I don't even know if it has a pedal, it might just have a lever. So there's a little butterfly valve up in there. Come up into the shot here. Okay, a little butterfly valve in there. And naturally, when you step on the accelerator, that butterfly valve would open. Okay, so no throttle position sensor was necessary for this thing. The carburetor knew what you did with your foot because the throttle opened, the airflow through the carburetor changed, and the mixture would therefore change. When we got away from carburetors, you might remember that one of our earlier fuel injection systems was this throttle body injection. So up in the top of this throttle, we have a couple of injectors that are going to squirt right down into the engine, right over our throttle plates. And naturally, this being an older system, there was still a throttle lever, there was still a throttle cable that connected your foot to this throttle body. Okay, while we're talking about throttle cables, this is a throttle cable here. This is actually a new one that's for my truck. I just haven't installed it yet. So this end here would clip onto the throttle lever on the engine. This would mount in a bracket. This little 2-bolt flange would bolt to the firewall of the truck, and the cable here would extend to the top of the pedal when you step on the pedal. You can see how that cable moves. Okay, so nice simple system. It's mechanical. Of course, you know what's going to happen to this cable. This is no different than a bicycle brake cable, only maybe a little less well made. Of course, over time it's going to wear in there. There's going to be some play or some slop, so you're going to get a little bit of a lag when you hit the throttle. Okay, but enough of the cable for now. More onto this TPS. On this side, our cable hooks up and opens the throttle. On the other side of that shaft, you notice this is a 2-barrel throttle body. I know Julio knows what this goes to because he's got one. Passes through and it goes into this sensor right here. This is your TPS, or your throttle position sensor. So as you learned yesterday, potentiometers have 3 wires. If we zoom in on that, you should be able to see 3 pins in there. I don't know which one is power, which one's ground, and which one's signal, but we could figure that out with a meter. And if you look underneath, you can actually see the little linkage of the lever that moves the sensor. Okay, so why does the computer need this sensor? Well, in the olden days of carburetors, we used to have this little pump right here that when we hit the throttle, it would shoot in a little extra squirt of fuel. And that was known as an accelerator pump. If we don't have a carburetor anymore, something has to take its place. So when you stab the throttle position sensor is going to report to the computer that you just opened the throttle, and it's going to know to add more fuel. This is also going to help with the operation of an electronic transmission. If you have an electronic automatic, this is going to have something to do with your shift strategy. So the computer wants to know where the throttle is, so it needs to know if it needs to downshift or if it's allowed to upshift. Okay, so the TPS plays a big role in air-fuel ratio management and also in transmission control in automatic vehicles. So it's kind of an important sensor. As time went on, the manufacturers developed the technology to eliminate the cable and go to what we call drive-by-wire, which you sometimes see abbreviated DBW. Drive-by-wire. And what that means is rather than a cable operating your throttle, wiring, electronics are doing it. So you're no longer stepping on a mechanical pedal, you're stepping on a sensor known as an APP, which is an accelerator pedal position sensor. So when you want to open the throttle, you step on the right pedal, the accelerator pedal position sensor reports that position to the computer, to the PCM, and then the PCM is going to open the throttle, not mechanically, but electronically with wires. And I just accidentally pulled one of these wires off my power supply. So I'm going to demonstrate this throttle body to you as soon as I get it wired back up. Hopefully I have these in the right place. If I don't, we'll figure it out. Okay, so you notice this throttle body has no lever, has no linkage, has no way for you to reach under the hood and rev the engine up. It's got the butterfly valve. You notice it's spring-loaded shut like a normal throttle, but it doesn't really close all the way. If we can see in the camera, there's quite a bit of light around that throttle plate. It actually holds itself open quite a bit. When this car is idling, the computer is actually going to physically close this throttle a little bit, and then when you request the throttle to be opened, the computer is going to open the throttle a bit. It's doing that with an electric motor, which is in here, and it's monitoring the position of this with, you guessed it, a TPS. Actually, 2 TPSs are built in here. So, we'll take a moment to discuss an old-fashioned TPS and a more modern TPS. Got a little graph to show you. Then we'll talk about this throttle body and how it works. So the TPS I showed you yesterday had 3 wires. This was a Ford one. It's not too different than the GM one right there. We know that one is a 5-volt reference. Then you have a resistor in there. Another wire is a ground. And your third wire is your signal. So this is fine for a conventional TPS on a drive-by cable or mechanical throttle. This will report to the computer where the throttle is, but remember, you've actually got a physical spring closing this throttle, you've got a cable opening it, so the computer's not controlling where the throttle is, it just wants to know where the throttle is. In this case, the computer's going to control where the throttle is, and therefore it really needs to know where the throttle is for safety purposes. So what we're going to do inside a more modern TPS on a drive-by-wire car is we're actually going to build in dual potentiometers. So it could have 2 ground wires, or it may actually combine those and only have 1 ground wire that they both share. It could have 2 5-volt reference wires, or again, it could combine them. But it's also going to have 2 signal wires. Signal 1, signal 2. And this is done for safety. When you do something multiple times just to make sure it gets done or for safety purposes, they call that redundancy. And by having 2 potentiometers working together as the throttle opens and closes, you've got some built-in redundancy, you've got some built-in safety. So I think you'd probably agree that it's pretty important to know where for the computer to know where the throttle is in its position so that it can accurately control it, because if it gave the the engine too much throttle opening, you'd get too much air, you'd get too much power, and the car could lose control. Or if the computer thought it opened the throttle far enough, but it really didn't, when you're trying to jump out in traffic and the throttle doesn't open far enough, you don't get the required amount of power, and you get creamed by a semi-truck. So that's a problem. You may notice, also, you may have noticed how I drew this. One of my signal contacts is down towards the ground, and one of my signal contacts is up towards the 5-volt reference. These signals, and I never labeled it, go opposite each other. They basically crisscross. So I'm going to dip into the ASE L1 composite vehicle manual here for a moment, so I can show you a graph. In the interest of time savings, their graph is much neater and tidier than mine. So you see here, TP1 at closed throttle, or zero throttle, starts out high and trends low, and TP2 starts out low and trends high. So they crisscross each other. So at 0% throttle, one of them is going to read 4.5 volts and the other one's going to read 0.5. And as you sweep the throttle open, these voltages will sweep opposite each other. At 100% or wide open throttle, TP1's reading 0.5 volts, TP2's reading 4.5 volts. So the computer's programmed to recognize this, and the computer knows that one is supposed to increase and one is supposed to decrease with throttle opening. But if it's constantly watching two, that's redundant, and that builds in a layer of safety for this system. So our APP our accelerator pedal position sensor. Unfortunately, I don't have a demonstration piece here. I don't have one here to show you, but basically it's a little sensor attached to the top of the throttle pedal. It's up under the dashboard of the car. It's a quick, easy thing to change if it fails. And much like a TPS, eventually it will fail because they're potentiometers, they're moving contacts. It's basically going to be built the same way, although not all manufacturers make them crisscross each other. Some manufacturers, they make them trend together, but they produce different voltages. So again, there'll be two potentiometers in there for safety or for redundancy. So when you request the car to go, it needs to go. When you pull your foot off the throttle in an emergency, it needs to stop accelerating. So this is important. So the example I'm about to show you would be drawn kind of like this. So notice how signal 2 is down very low, close to ground, and signal 1 is a little bit higher up. So basically one starts at a slightly higher voltage. And again, we'll refer to our ASE composite vehicle book just to give you an example. Their graph is much prettier than mine would be. Okay. APP1 at 0 accelerator pedal position produces 0.5 volts worth of a signal, and that's going to sweep all the way up to 3.5, whereas APP2 is going to start at 1.5 at 0 throttle and trend all the way up to 4.5, and we can see that in this graph right here. So 0% applied throttle pedal or accelerator pedal, 0.5, 1.5, 100%, 3.5, 4.5. Okay, again, done for redundancy. So if you're not sure what I'm talking about here when I say composite vehicle, this little booklet right here is what they call the ASE composite vehicle booklet. And if you go to take the L1 engine specialist test, this is like a service manual for a car that doesn't really exist. It's a car that ASE built and made up in their minds kind of, and they call it the composite vehicle. And basically what that does, if you go to take the ASE L1 test, they don't want a Toyota tech to have an unfair advantage if the vehicle that they're using on the test too closely resembles a Toyota versus a Ford or versus a Mazda. Basically, they don't want to give someone an unfair advantage. So that's why we use that right there. Not actually sure if I should be using that. I know I would normally in my classroom. As far as this video here, well, I guess I'm going to have to keep it set private in the playlist. Okay, so hopefully no questions on APP and TPS sensors. They're just basic potentiometers. A couple other quick things we should probably mention. Why did we bother going to drive-by-wire systems in the first place? What was wrong with the old cable? Well, I think you can all agree a mechanical cable is eventually going to wear, so going to drive-by-wire eliminates a wear item. You might be thinking, yeah, well, the electronics in this drive-by-wire throttle body are going to wear, and in our accelerator pedal position, they're going to wear. And you're not wrong, there are different wear items, but this does allow us a little bit more control. When I say us, I really mean the PCM. The PCM is now fully in charge of that throttle, and what that allows us to do is simplify a few things. First of all, on fuel-injected engines that don't have drive-by-wire, you need an extra little actuator here known as an idle air controller. This can be eliminated if you're moving the throttle constantly. So what this idle air controller does, and we'll go over this in greater detail in another video, this is what actually allows the air into the engine at idle. These throttle plates close almost completely. But if you have a drive-by-wire engine, the throttle is being continuously moved and controlled by the PCM. You don't need an idle air controller. So there's some wiring and an actuator that can be eliminated, and also a driver in the computer and some programming that can be simplified. So that's a part we can get rid of. So no IAC, or idle air controller. Likewise, you may have been driving on the highway once and thought, I don't want to keep stepping on this pedal. I've got another hour on this highway to go, and you set something called cruise control. In the olden days, cruise control was accomplished by a separate actuator. There had to be another piece on the car under the hood, either a vacuum-operated device or an electric motor-operated device that would hold this throttle at your set point, and then looking at the vehicle speed sensor as you slow down because you hit a hill, open the throttle a little for you, or if you start to speed up because you're going down a hill, close the throttle a little for you. So that's a whole other mechanical device that can be eliminated and simplified, because we can do that directly with our throttle. So no cruise control servo. So that's simplified. Earlier in the year we talked about ABS and traction control systems. When you're starting to get into a skid or get out of control, your traction control may want to take over, and it's going to have a much easier time doing so if it can back your dumb foot off the throttle and take control of the engine. So basically easier traction control management. And the most important reason for switching to drive-by-wire, emissions controls. By having better control over the air entering the engine, we have better control over our emissions. So really, this is the ultimate. Emissions and fuel economy are going to be better with drive-by-wire throttles, as well as eliminating some extra stuff we didn't really need anymore, like an idle air control, an IAC, or a cruise control servo. Okay, so one more acronym to throw your way before we move down to the bench and actually watch this little drive-by-wire throttle operate, and that's TAC. So this actual throttle body here, the unit inside here, the actual electric motor that operates the throttle and makes it move, and makes that neat little snappy whirry noise. You're actually hearing the gears and the spring work in there. Is your throttle actuator. It's supposed to be a U actuator control. So an actuator is something that causes an action. Basically, it makes something happen. So this is the muscles of your PCM. The sensors are the senses, and the actuators are the muscles doing the work for us. So get set up on this bench here, and you can take a closer look at how this throttle actuator actually works. I think we might even finish this video on time. Not have to have a part 2. So, I reach over here. We have our trusty variable power supply, and you notice I have it turned way down low, 2.9 volts. Make sure our jumper wires are still in place here because I don't want to make a short circuit. And let's see if we can set this up so that you can see it. Well, I guess that's probably going to be. We'll prop it up against the old GM throttle body here. This is actually a GM throttle body also. Alright, so if I have my polarity correct, and I do, when I connect my jumper wire here, you can see that throttle begin to open, and you might notice it's opening kind of slowly. If I can shine a little bit of light in there, make our view a little better. You notice how slowly it's opening? Remember, I have my power supply set at 2.9 volts. If I increase this voltage a little bit, bring this up to 5 volts. Notice it opens a bit quicker. You also notice that even at 5 volts, it goes to wide open. I'm going to bring this right up to 12.6 volts. So what you could expect to find key on, engine off. It opens pretty darn quickly. Okay, if I peg this thing right up at 14.5 full charging voltage, tell me what you think about this. Let me get my jumper leads in here so you can kind of get an idea of how quickly this happens. It's pretty quick, I think you'll agree. So, a lot of people complain about drive-by-wire throttles because of what they call lag. Let me prop my camera back up here. Again, looks like we've got about 3 minutes before this thing splits us off into a second video. So, people complain about drive-by-wire throttles because of lag. They say that they don't respond fast enough. Well, I'm here to tell you it's not the actuator, it's not the TAC that lags, it's not the APP that lags, it's the computer programming. So you got to remember, most street vehicles are designed for people that want to go to the grocery store, drive like sane human beings on the roads, and mostly obey the speed limits. When you want to take one of these vehicles to the track, you might find that the lag that they build in from the factory in the computer programming, basically in the response they program in, is not to your liking, or even for some spirited driving on the road, you may not like how that feels. But I'm here to tell you that a drive-by-wire throttle is more than capable of performing just as quickly as a cable-operated throttle, maybe even quicker. And the last thing I should mention, something known as PWM, or pulse width modulation. We're going to discuss this in detail in another video, but I want to make clear that the computer is not sending 1 volt to this throttle to make it open a little bit, or 2 volts to the throttle to make it open a little bit more. You notice that 2.9 volts even, that throttle opened wide open. The reason for that is the computer actually pulses or modulates pulses of voltage to that throttle, and I cannot duplicate that here on my bench. But the pulses that it sends are how we actually get that throttle to open up quickly and then stay at an exact spot. So let's say you want to accelerate and then hold the throttle at 30%. It's going to send voltage to that motor to open that throttle to exactly 30%. It's going to know it's at 30% because there's a pair of TPS sensors built in here. And then it's going to hold its pulses at whatever modulation it's sent to that TAC to get it to that 30%. It's going to hold it right there, and that's how it maintains the throttle position. So we're going to discuss pulse width modulation in another video. All right, I'm going to walk back over to this camera and shut it off now. I'm hoping that it hasn't flipped over into another video. If so, I'm going to have to go back and finish this one. So anyways, this about wraps it up. This is all I really had to say about drive-by-wire throttles. Hope you enjoyed the video. Have a good night.